Computers are incapable of understanding language. They only compute numerical relationships. To see how generative AI actually functions, we must discard high-level analogies and trace the exact mathematical sequence of a single input token executing a forward pass. This is GPT-2 small, our baseline. It operates on 3 constraints: 12 transformer blocks, a 768-dimensional vector space, and a 50,000-word vocabulary limit. We'll use the sequence "a true friend accepts you," isolating focus on the third index, friend. We will track exactly how this word is dismantled into numerical values, refined by the mathematical context of its neighbors, and used to predict the next word in the sequence. This architecture functions as a structured discrete to continuous to discrete mathematical pipeline. The very first processing step is isolation. The model strips the input string of its sentence structure, treating every individual word as a fully independent entity. This is a byte-pair encoding lookup table, a static 50,000-entry dictionary where the model matches characters, subwords, and full words to unique integer values. Here, our target word friend is permanently mapped to a specific integer ID. In this model's vocabulary, that ID is 2012. At this stage, the integer ID contains 0 semantic meaning. The integer 2012 is merely an arbitrary database key used for identification. It is not a mathematical representation of what the word actually defines. Before the neural network can process the concept of friendship, the architecture must convert this arbitrary integer into a spatial, continuous representation. This is the token embedding. The integer 2012 passes through a matrix and expands into a dense, vertical array of 768 floating-point numbers. These dimensions represent semantic traits, encoding grammatical roles, emotional weights, and conceptual relationships derived from the model's training data. However, this token embedding contains no data regarding where the word is located in the sequence. Without strict order, the sentence is just a bag of words. To restore order, the architecture generates a positional embedding, a separate 768-dimensional vector encoding the word's location at index position 3. The model performs a vector summation, merging the token and positional arrays into a single, unified 768-dimensional input embedding. This merged vector is the true starting point for the neural network, a mathematical object containing both the definition of the concept and its exact coordinates in time. The vector now enters the transformer block. In GPT-2 small, it will loop through this exact refinement process 12 separate times. It begins with layer normalization. The vector's values are mathematically constrained so the mean is 0 and the standard deviation is 1, preventing extreme numerical variations from disrupting the calculation. This allows for multi-head attention, the mechanism where words interact. Through these connections, the vector updates internal values, creating a precise context map. To prevent overfitting, the dropout layer randomly deactivates values. This forces the network to distribute learning across all 768 dimensions, rather than relying on dominant signals. To ensure the original token meaning isn't lost across deep networks, skip connections provide an alternate path, allowing raw data to bypass certain layers and effectively maintain the vector's overall stability. While attention provides a context map of the sentence, the vector's values are still limited by their original semantic definitions. It has finally identified its closest neighbors, but it has not yet processed those relationships through the higher-order transformations required for pattern recognition. Following a second normalization step, the vector enters the feed-forward neural network. Here, the model performs a geometric expansion. The single 768-dimensional vector is projected into a 3072-dimensional space, allowing the network to explore much more complex linguistic features. Once these higher-order relationships are mapped, the network compresses the data back down to exactly 768 dimensions. A final dropout layer and skip connection complete the loop. The vector must now repeat this entire gauntlet 11 more times. A critical rule of this architecture is that throughout all 12 blocks, the physical dimension of the vector never exceeds 768. It is the density of context stored within its changing values that grows, making the representation more refined with every pass. After exiting the final transformer block, the vector passes through one last layer normalization to stabilize its final mathematical state. We now face the final hurdle. The model possesses a highly intelligent floating point vector, but the user requires a discrete English word. This final stage uses the output projection layer, a matrix mapping the continuous vector space back into the discrete vocabulary. The 768-dimensional vector is multiplied by this matrix, expanding into a 50,000 value array. This forms a probability distribution across the entire vocabulary. To select the next word, the model uses a function called argmax, which simply identifies the index with the highest numerical value. In our sequence, that specific high probability index maps back to the word accepts. Through vector summation, dynamic attention, and consistent dimensional constraints, the model has mathematically deduced the most logical subsequent concept. While frontier models introduce new routing and scaling efficiencies, this fundamental pipeline remains the structural standard for generative artificial intelligence.